Good morning. Hope everyone's doing well. I figured it would be a little sparser this morning because of it being Thanksgiving week, but there's only three of you. Hi, Gabriella, Harley, and Leanna. That's all we got. Um, well, if you guys, while we're lecturing, if y'all have specific questions on anything, we can stop, sort of take it slow. We finished up gas laws last week, so this week we're going to move into solutions. So chapter 13 is all on solutions. There's only two more chapters left. It's chapter 13 and chapter 14. Chapter 13, solutions. Chapter 14 is acids and bases and buffers. And these two chapters they really go hand in hand. You can't really do acids and bases without having a good understanding of solutions. So let's see, just for your information, the tragedy at Lake Nyos in West Africa. So there was this lake in Cameroon that it was a really, really deep lake. And it had a lot of buildup of carbon dioxide. And because the lake was so deep, it created a really high pressure system. So the column of water was able to keep a lot of the gas in solution. So it was kind of like a bottled up can of soda pop. So there's all this CO2 dissolved in the water. At one point, the lake was disturbed, which means that the lake kind of turned over, and all of that CO2 was released from solution. So sort of like that idea of when you open up a can of soda pop, it releases the gas. And this lake was sitting on top of a hill. So all these little CO2 molecules boop, pop out of solution and start to roll down the side of the hill. Why does it kind of roll down the hill? Because CO2 has a molar mass of 44, which is heavier than oxygen or nitrogen or any of the other gases that you would find in the atmosphere. So CO2 is normally a relatively harmless gas, right? It's what we exhale. But if you have large quantities of it, it can suffocate people pretty much because they're not able to get enough oxygen. So all of this CO2 rushed down the side of the hill, and it killed more than 1,700 people and it's like 3,000 cattle. So they call it the tragedy at Lake Nyos. So what they've done since then, right, that was in like 1986. What they've done since then is they've installed these depressurization systems that help to control the release of CO2 so that they don't get a huge buildup anymore where they could have this sort of mass killing event. So how that relates to solutions, well, the carbon dioxide and water mixture at the bottom of Lake Nyos is an example of a solution, specifically a homogeneous or homogeneous mixture where it has two or more substances. So it has water, there's probably some trace amounts of like solids dissolved in there. And then it had this CO2 gas. And you couldn't, when you're in a solution, the states of the two mixtures become the same. So in this case, the gas was sort of hidden within the liquid water. The ocean is an example of a solution. This is a solid with a liquid. So we have salt dissolved in water. We've got blood plasma, which is a combination of liquid with a couple different solids. And there's also some gases in there as well. So all different sorts of ways that we can have solutions. So gaseous, we can have gas-gas mixtures, that's air. We can have gas and liquid, that would be like soda water, CO2, combined with H2O. That's what gives soda water, soda, that like enjoyable effervescent quality is that there's CO2 dissolved in there. Liquids and liquids, the example they give vodka. So, right, any alcohol when you buy hard alcohol, it'll say 70 proof, right? You're not ever buying 100% alcohol. It's always diluted to some extent with water. Solids and liquids, so that's seawater. And what you can see is anytime you're dissolving a gas, a liquid, or a solid with a liquid, it will always move towards the solvent phase or whatever is doing the dissolving. And we can also actually have solids, solid solutions. So something like brass or different metal alloys, where brass specifically is copper and zinc mixed together. But there are other alloys where we have two different metals that we mix together so that we can find, or we can have a material that has the properties of two things. So it's kind of like you get more bang for your buck in the metal. So when looking at a homogeneous mixture, specifically a solution, it will have at least two components. The majority component is usually called the solvent, and the minority component is called the solute, okay? So solute plus solvent gives you solution, simple equation, right? Whatever the mass of the solute is, plus the mass of the solvent will give us the solution's mass. In a solid liquid solution, the liquid is usually considered the solvent. So do note that if we are having any sort of salt dissolving in water, it doesn't really matter how much of each we have. It's to determine what's the solute and the solvent. The liquid will always be classified as what's doing the dissolving. And then we actually have a special group of homogeneous solutions known as aqueous solutions. This is anything where we have a material dissolved in water. And why do we have a group just for aqueous solutions? Well, water is so abundant on Earth. We find it everywhere. So it would make sense that we would have a specific group of solutions just for water. There are chemists out there that study just aqueous chemistry. They only look at things happening in water solutions. There are actually aqueous geochemists, which are chemists who look at geology and they only look at water solutions of geology. They ignore everything else. So this is a very, very important field. There are other solvents out there. So water is a polar solvent, right? That means that it's a polar molecule. It will break apart polar things. But sometimes we need to dissolve nonpolar material, things that are really balanced in their Lewis structures. They don't have lone pairs of electrons. So there are some nonpolar solutes that we would expect to find in a lab setting. So here are some of the common polar solvents. What you'll notice about them is they're all sort of asymmetrical, or they'll have lone pairs. So this acetone here has this CO group here. The carbon is double bonded to this oxygen. Methyl alcohol, all the alcohols that are shorter like this are going to be polar. This OH gives this thing some asymmetry. Sometimes instead of methyl alcohol, this will be called methanol. These are all our nonpolar solvents. There's more than just these, but these are the examples we have. So really balanced structure here. Diethyl ether, yes, there is this sort of different oxygen, but this thing is getting much longer. So we would actually say this is nonpolar. This here also really balanced. Now, we don't get into organic chemistry right now. So if you're looking at this and you're saying, I can't see a difference between what's going on over here and what's going on over here, that's okay. I'm not gonna make you identify, I'm not gonna give you like diethyl ether and say, is this, you know, polar or non-polar? But do know that water is a polar solvent. And just know that loosely, like likes dissolve likes. So polar things will dissolve polar solutes. Non-polar solvents will dissolve non-polar solutes. So how do we dissolve a solid in water? Like if I take NaCl and I stick it in a thing of water and I stir it up, why does the salt, you know, sort of disappear? It's not disappearing, but what's happening is we've got this NaCl, okay, and normally the Na and the Cl are connected to each other in that three-dimensional lattice structure. But water is a polar molecule, which means that it has these dipole moments, or it has a part of it, specifically the oxygen side, where there's sort of a negative charge. And on the hydrogen side, there's a positive charge. And this dipole moment is so strong that it's actually stronger than the connection between the Na and the Cl, or the solute-solute attraction. So it will start to pull apart the Nas and the Cls, kind of breaks them up. So here we've got our salt, and the water will kind of cling to the outer parts of the salt and start pulling off NAs and CLs. If you have a big hard hunk of NaCl, it's going to take a lot longer to dissolve because there isn't much surface area. If I was to break this up or powderize it and then drop it into water, it would dissolve much faster because there'd be more spaces for the water to kind of pull these things off. So once we've dissolved our salt or put it into solution, you can kind of think of it as your Na plus and your Cl minus. They're now charged particles. They're not combined in this lattice structure to give us a neutral charge. They're actually charged particles, or they're electrolytes, and they're surrounded by these water molecules. So they're this chlorine is kind of buffered by all these little hydrogens, and this Na is buffered by all these little oxygens. So they can't get back to each other or recombine. Now, if I was to, let's say I was to heat this solution up, what happens to these water molecules is they evaporate, and the chlorine and the sodium will be left behind, and they can actually recombine. And that's when you get your precipitate, or you can get the crystalline NaCl forming at the bottom of the beaker. So here we've got NaCl. When it's in its molecular form, it's going to be combined. But when we drop it into solution, it breaks apart into its ions, Na and Cl. So that shouldn't be too new for you, especially after doing the reactions chapter. The Na and the Cl will be evenly dispersed throughout the water. And then the water molecules will surround each of the ions. So how much salt do you put into water? It's kind of dependent on, what your desired effect is. So water at a given temperature can hold a certain amount of salt. This is known as the material's solubility. So the solubility of sodium chloride at 25 degrees Celsius, and it is based on temperature, because if I increase the temperature, I can actually hold more salt. If I decrease the temperature, I hold less. So the solubility of sodium chloride at 25 degrees Celsius will be 36 grams of salt in 100 grams of water. If we reach this point, if we're holding the maximum amount of salt in the water, we would say that this is a saturated solution. So like when you go out for a run in the rain and you come home and you're saturated in water, your clothes are completely filled with water. You can't hold any more water. Well, this solution is completely saturated with salt. It can't hold any more salt. So in a saturated solution, if I was to add more salt to that solution, the salt would just accumulate at the bottom of the container because it can't be held. If I wanted to dissolve more of the salt, I would have to either heat the solution up or I would have to add more water. An unsaturated solution is anything less than that maximum amount. So whereas a saturated solution, you hit that point, it's 36 grams for every 100 grams. An unsaturated solution can be quite a large variety of solutions. So anything less than 36. So 35 grams would be an unsaturated solution. 1 gram in 100 grams of water would be an unsaturated solution. 21 grams of water, right? There's a plethora of options. 35.599999 would be slightly unsaturated. Then we have this fun kind of solution, which is known as a supersaturated solution. This is one where you're holding more than the normal amount. So like 30 in this case, maybe 37 or 38 grams of salt in 100 grams of water. You're actually holding more of it. How you can get a supersaturated solution, there's a couple different ways, but one thing you can do is you can heat the water up, pack it with salt, and then very slowly cool it back down. And sometimes you'll get this case where the water will hold more salt. But the thing is, it's a very unstable situation. So the solute will normally like to precipitate out, especially if you put like one little grain of salt in that supersaturated solution, a lot of the salt will come out. So it tells us other examples of a supersaturated solution. We can have a can of soda. So when you open the can of soda, it's a supersaturated solution. There's more gas than what it should be holding, but it will release that material, specifically the CO2, until it becomes just a saturated solution or an unsaturated solution. So the solubility rules give us a qualitative description of the solubility of ionic solids. So remember, the solubility rules tell us what can dissolve and what. So, you know, if we have certain things like calcium carbonate, we would say is insoluble based off of the solubility charts. Why? Because the calcium and the carbonate have a much stronger bond to each other than the attraction to them to the water. So it's harder to pull them apart. So the solubility of calcium carbonate is close to 0 grams in 100 grams water. You may find 1 or 2 that are, you know, popped off from each other into the ionic form, but in general, they tend to be, they stay in molecular form. Molecular solids may also be soluble in water, depending on whether they're the solid is polar or not. So table sugar, this thing right here, is polar. It's not very balanced structure. It is soluble in water, so it will dissolve in water. There are other things that are not polar that are insoluble. So things like lard, vegetable shortening, butter, you know, olive oil, those sorts of things. If you dump those into a container of water, they're just going to kind of glob up. So it is important to know the difference between an electrolyte solution and a non-electrolyte solution. So on the left here, this is dissolved sodium chloride. Remember, when you have a salt like this and you put it in water, it breaks apart into its ions, which gives it a charge, or there's charged particles, so we can run a current through this. That is different than what's happening with dissolved sugar. In this case, this is a molecular structure, so not ionic. It's not a lattice structure of positive and negative charges. It's these complete molecules that simply break apart from each other, but they themselves are not breaking up. So the molecules stay a little packet. In that case, then we don't have these positive and negative charges. We just have molecules globbing around. I can't run a current through it. So we would say it's a non-electrolyte solution. So you could electrocute yourself in a salt solution. You wouldn't be able to electrocute yourself in a sugar solution, assuming that there's nothing else, no other impurities in there. So as far as, and I've already kind of touched on this, but solubility with temperature. So in general, and this only includes solids in water, it's not gases. And in general, solids, their solubility will increase. So here's on the y-axis, we have solubility. On the x-axis, we have temperature. So as we increase the temperature, the solubility will also increase, or I can dissolve more salt in the same amount of water if it's a hotter water solution. You notice here, table salt is actually relatively stable. I mean, we do increase our solubility slightly as we increase temperature, but nowhere near as much as some of these other ones. I mean, look at KNO3, man, that thing is like, boom. We add a little bit of heat and we're going to be able to dissolve a lot more of it. Using temperature dependence of solubility to purify compounds. So one thing you can do if you want to purify a material is this thing called recrystallization. So what you do with recrystallization is you take a solid, you dissolve it in water, or you can use a different solvent, and you increase the temperature. So you heat it up. You pack a bunch of salt in there, or a bunch of whatever the material is that you want to purify. And then you let the solution cool down. And as the solution cools down, you get this precipitate. And usually the precipitate that comes out of solution will be purer than the material you started with. So let's say we dump salt in water. Sometimes that salt will have like little impurities, little ickies that have gotten in there throughout the refining process, or maybe they just pulled it out of the side of a hill or something like that. Well, we can purify it really simply doing that. This thing here, rock candy, I don't know if anyone's ever eaten that stuff before. I find it absolutely disgusting because it's literally just sugar. And we spend so much for it, and you can make rock candy like at home. It's just a recrystallization process. So you make a supersaturated solution of sugar, and you can use table sugar. I mean, that like big bag of sugar that you bought from Walmart for like $1.98. And you dangle a string inside the solution, the supersaturated solution, and you let it cool for a few days. Well, the sugar will start to recrystallize or grow on the string, and then voila, now you have this rock candy that you can then charge like $8 for. So whatever. All right, solutions of gases in water. So these are cool solutions, right? You're taking a gas and then you're sticking it in a solution, and the gas will actually it almost seems like it hides. It's no longer a gas, but it turns into this liquid solution form. So the water at Lake Nyos and also a can of soda pop are both examples of carbon dioxide being dissolved in water. In general, most liquids that are exposed to air contain some dissolved gases. So if you have a cup of water sitting on the countertop, that will have a certain amount of dissolved gas to it because the atmosphere around us is exerting a pressure and it's dissolving some of the gas in it. Our blood contains dissolved nitrogen, oxygen, and carbon dioxide, right? We're taking the nitrogen and oxygen in, we're releasing the carbon dioxide out. Tap water also has different atmospheric gases dissolved in it. You can see the dissolved gases in ordinary tap water when you heat the water on the stove before the water reaches boiling point. Okay, so we're not talking about that rapid bubbling. That's a phase change. But right before that, when you get those little bubbles that develop at the bottom of the pan, that is actually dissolved gas that's releasing out. Why is it releasing? Because we're heating it up. It can no longer hold that gas. So where is it? So along with that, seeing those little bubbles, there's a rule on solubility that says that as you increase the temperature of a solution, you will decrease its ability to dissolve gases. So this is the opposite of solid, right? If I have a hotter water solution, I can dissolve more solid. But if I have a hot water solution, I can dissolve less gas. Example of this, so think about how you like to drink pop or beer or whatever. We tend to serve it cold versus warm. Why? Because a cold pop has a lower temperature. It can hold the dissolved gas for longer, or it can hold more dissolved gas. So this cold will have a much more effervescent quality to it. Warm pop, the carbon dioxide in it wants to escape because it's warm. So we're going to see lots of bubbles coming out of solution. That's going to get flat very, very quickly. So I guess if you like flat pop, then go ahead and drink it warm because it'll get there much faster. Another way that we can increase solubility of gases in a solution is this thing called Henry's Law, which says that if you have a higher amount of pressure sitting above whatever the liquid is, you'll have more dissolved gas. So this can be thought of as a closed can of pop. There is a pressurized head in that can of pop. There's lots of gas packed in there, more collisions. It will allow more dissolved gas. When I open up that can of soda pop, the gas that's in that confined area can now escape. So it will lower the pressure and we will see less dissolved gas in solution. So your can of pop will actually stay fizzy once you've opened it. It'll stay fizzy longer at sea level than it will up on the side of a mountain because of that difference in atmospheric pressure. So there we go, closed. All the CO2, it's under pressure, so lots of CO2 dissolved, very fizzy, yummy pop. We open it up, we release the pressure, and now the CO2 bubbles will come out of solution because of Henry's Law. So solutions are different than chemical formulas. I mean, solutions contain chemicals, so they will contain chemical formulas. But when you have like, for instance, sodium, one second. Okay, when you've got sodium chloride, NaCl, this is a compound and it has a specific formula, right? So if I want to make sodium chloride, I need a sodium with a chlorine. That doesn't change. Solutions are different. A solution would be like salt water. So salt water. This contains NaCl and H2O. Now, in this case, I actually can change the amount of salt relative to the amount of water, or we can affect what's known as its concentration. So does it have a high amount of salt, a high concentration, or a low amount of salt, a low concentration? So whereas NaCl, we never would have to talk about a compound or a formula having a certain concentration because it has a built-in rigid formula that we have to use. Solutions, we have to tell the reader what its concentration is, because a solution that has a very low concentration versus a solution that has a very high concentration can have super detrimental effects, right? Taking a bath with a little bit of salt in it to ease your muscles versus taking a bath with a high concentration of salt that could start to burn the skin. So you want to make sure that you know your concentrations. We have a variety of ways that we can talk about concentration. One is mass percent. And this one should feel pretty, you should feel pretty comfortable with this because we've already gone over mass percent. But mass percent is the number of grams of solute per 100 grams specifically of solution. So that's the thing that I want to really put into your brain is when we're talking about concentrations, the denominator is always going to be referring to the solution as a total, not just the solvent, not just the thing that's doing the dissolving, but the total amount. So a solution with a concentration of 14% means that there are 14 grams of solute in every 100 grams of solution. To calculate it, we take the mass of the solute and divide it by the, again, solution, which is solute plus the solvent. So here is our equation for it. Again, they even put in the notes here, they say, note that the denominator is the mass of the solution, not the mass of the solvent. So I'll give you all one to work on. Let's say, what is the mass percent of a solution made by mixing 33 grams of KCl with 95 grams of H2O. I'll give you 3 minutes for that. Okay, so what is the mass percent of a solution made by mixing 33 grams of KCl with 95 grams of water? So mass percent is going to equal mass of solute over mass of solution times 100. And this mass of solution is mass of solvent plus solute. So when calculating this out, my solute is the 33 grams of KCl. My bottom denominator is going to be the 95 plus the 33. So we take them both into account and we multiply this thing by 100. And we end up with, let's see, let's go with 2 sig figs, so 26%. If you didn't include the 33, if you just real quickly said, oh, this divided by this, you're not going to end up with the right number, okay? Your mass percent will be too great. Let's do one asking for a different variable. So how many grams of NaCl are in 225 grams of a 12% solution? How many grams of NaCl are in 225 grams of a 12%, specifically a 12% NaCl solution? We'll give you 3 minutes for that one. And obviously, if you're having trouble, just ask me. Okay, so this problem is asking us to find out how many grams of the solute or the salt do we have in a known amount of solution, and we know what its concentration is. So we can use the above equation and just sort of rearrange. If we look at this thing here, we know this and we know the total amount of solution we have. So we're just trying to find that top value. So I'm going to go ahead and plug that into the equation. So I have 12%, because I've got that there, is equal to, well, we're trying to figure out grams of NaCl. We know how many grams of the total we have, 225 grams. And this whole thing is multiplied by 100. So we'll divide by 100, divide by 100, or move the decimal over 2 places. So 0.12 equals grams of NaCl over the 225 grams of solution. So we'll multiply those two together. And know that your solute should be less than your solution, right? The thing that's getting dissolved should be less than the total solution. If that doesn't happen, you may have gone awry somewhere. So this will then equal 27 grams of NaCl. Sometimes they'll use this as a conversion factor. So 12%, if I have a solution that's 12% NaCl, that's the same thing as saying that I have 12 grams of NaCl in every 100 grams of solution. Okay, so now I've got this thing that I can use as a conversion factor. So I start with my given value of 225 grams of solution. And I just multiply it by this thing here that's 12 grams of NaCl over 100 grams of solution. And what you find is that the grams of solution will cancel and you're left with 27 grams of NaCl. You get the same answer either way. If you like to use conversion factors, you may want to go that route. If you'd rather just plug it into the equation, no problem with that. So this is known as mass percent. There are other ones besides parts per 100. Sometimes we refer to this as parts per 100 because in a lot of solutions, there's really teeny tiny trace amounts of things. So sometimes we'll go with parts per million, which is, the number of grams that we would expect to have in 1,000,000 grams of solution, or we have parts per billion, which is the number of grams in 1,000,000,000 grams of solution. Why would we care about some of these really small concentrations? Because some materials, even in these very small concentrations, like mercury, for instance, can be detrimental to people. So we want to know, hey, how much mercury is in the water? Parts per 100 is not enough. If there was one gram in 100 grams of mercury, we'd all be very, very sick. But we could get sick even if it's down to the parts per million. So using mass percent in calculations, right, we can use it as a conversion factor. I don't really like this problem, so we're going to leave that. Okay, so let's talk about some other types of concentrations. We have this thing called molarity. This one is used most of the time. So when you're in a lab setting and you have 6 molar hydrochloric acid, it'll have this big M next to it. Molarity is the number of moles of solute per liters of solution. So don't get it mixed up with moles. It is related to moles. As the number of moles goes up, your molarity will go up, but molarity is not an amount, it's a concentration. So it's going to be amount per liters. And it also says, make note, this isn't just liters of the solvent, it's liters of solution. So it's both materials. So how do you make, let's say we wanted to make a 1 molar NaCl solution. 1 molar or 1 big M means that we have 1 mole of solute in a liter of solution. So if I was to make that, I would put 1 mole of NaCl in a flask, which is 58.44 grams. Those are really easy to interchange just using our periodic chart. And then after I put that salt in, then I would fill it up to 1 liter to dissolve it. And the ending result would be 1 liter of solution. What you don't want to do is put in a liter of water first and then add the salt. Why? Because then you would end up with more than a liter, right? The salt's going to displace some of this and your solution will actually be bigger. So you always want to add the solid first and then dilute it to whatever volume it is that you're desiring. So here we've got a problem. Calculate the molarity of a solution made by putting 15.5 grams of NaCl into a beaker and adding water to make 1.5 liter of NaCl solution. So I'll give you guys 3 minutes for this one. Note that this is giving you grams and molarity is moles per liter. So you got to do a little converting. So I'll put on here molarity. Come on. Molarity equals moles over liter. All right. So you guys have a couple minutes for that. All right, so in this problem, we want to find molarity equaling moles per liter. We're given the mass of NaCl, but it's in grams, and then we know the liters of the full solution. In order to use molarity, we need to have moles and we need to have liters. So we're almost there. We do have liters, so I don't need to convert that, but I need to go from grams into moles. And that, hopefully that feels like second nature now. You know, you just find the molar mass of NaCl, which is 58.44. So we take our 15.5 and setting it up in dimensional analysis, we'll divide it by the molar mass and we get 0.2652. We take that value and we divide it by the number of liters in this solution, and we end up with 0.177 molarity, or big M. Looking at this one here using molarity and calculations. So this one here says determine how many grams of sucrose, your sugar, are contained in 1.72 liters of a 0.2758 molar sucrose solution. So in this case, they give you molarity and they give you volume, and they want to know grams. Now, molarity and volume aren't going to give you grams, they'll give you moles. So then we can go from grams to there. So here they've got liters of solution, they're going to get you to moles of the solute and then grams of the solution. So how do they do that? Well, they take liters of the solution, right? We're given 1.72 liters, and they multiply it by its molarity, but the molarity looks different here. Over here, they gave us molarity and they said, hey, I know that this thing is, it's a 0.758 big M. But this is the exact same thing as saying 0.758 moles, specifically of the sucrose, so C12H22O11, divided by 1 liter of solution. So if you're plugging it into the equation, you know, you're writing out molarity equals moles per liter, then you'll use this value. If you want to do it in dimensional analysis, you'll use this value, which is what the slides did. All right, so I'll show you how they did that, and then I'll give you guys a secondary example you can work on. So they decided, instead of using it and plugging it into equation, they were going to set it up in dimensional analysis. So that's where this 0.758 moles of sucrose for every 1 liter of solution happened. What will happen is the solution volume will cancel and you're left with moles of sugar. And then you just use the molar mass of your sucrose. And this time we'll put the moles on the bottom and the grams on top, and it'll give us the grams of the final amount. So I'll give you another one. And again, you're more than welcome to solve it in dimensional analysis or solve it just by plugging it into the equation. It will give you the same answer as long as you're doing them both correctly. So how many grams of MgCl2 are in 18, no, I don't want to go with, do something a little bit different. 2,300 milliliters of a 0.153 molar solution. All right, I'll give you a couple minutes for that one. How many grams of MgCl2 are in 2,300 milliliters of a 0.153 molar solution? So it's very similar to that last problem we just worked on. If you want to use it, that is your basis. All right, so let's finish this problem up and then we'll call it a day. So how many grams of MgCl2 are in 230 milliliters of a 0.153 molar solution? So we were talking about molarity. If you want, might help to just write out molarity equals moles over liters. I'm going to plug it into the equation this time. So I have this value, right? It's this thing over here. So 0.153 big M is equal to moles. I don't know moles over liters. Well, this is in milliliters. So let's get this into liters. Move the decimal over 1, 2, 3. We're going to be at 2.3 liters. So I can solve for my moles just by taking that 0.153 and multiplying it by the 2.3. And we get that we have 0.3519 moles. And specifically, it's moles of MgCl2. Now, the problem doesn't want it in moles, it wants it in grams. But again, those two things, grams and moles, really easy to hop back around because we know that every 1 mole of MgCl2 is equal to, let's see, I didn't grab that one. Molar mass of MgCl2 is going to be 95.211 grams. Moles will cancel, so we're just going to take our number of moles and multiply it by 95.211, and we get, this thing will equal 33 sig figs 1, 2, 3. This, the way that this is written, it only looks like we have 2 sig figs. So instead of 33.5, I'm going to go with 34 grams of NaCl. No. Of MgCl2. And we're done. Okay, could you have done it in dimensional analysis? Sure. Why don't I just run through it real quick? You start with your volume, but your volume needs to be in liters. So we've got 2.3 liters of solution. And I'm going to multiply that by my molarity. Now remember, molarity, this is the same thing as saying 0.153 moles for every 1 liter of solution. Those are the same things. So I'm going to put the 1 liter of solution on the bottom and the 0.153 moles of the MgCl2 on the top. Liters of solution will cancel. Again, the problem doesn't want it in moles, so we're going to multiply this by its molar mass, 95.211 grams for every 1 mole, specifically of the MgCl2, cancels, and we will get the same answer, 34 grams of MgCl2. So you choose how you like to do it. All right, so we'll stop there. We are not meeting on Wednesday. So go ahead and enjoy a nice, well-deserved break, because when you come back, things are going to move pretty quickly. We will have really just a few weeks before finals. So if you have any questions, feel free to stay around and ask me if there's anything you want